As I said at the end of the previous recording, I'm going to take this example that I did with a proton being fired into a uniform magnetic field, the proton being fired to the right in what I've defined to be the positive y direction. Our magnetic field is pointing in the positive z direction. And what I've done, as soon as I move aside, you'll be able to see it, is I've taken this entire diagram and rotated it into the board. So actually I've rotated it like this. And so here we go. First of all, take a look at the coordinate system. As I said, I rotated it like this. So now the positive z-axis is pointing into the board. The positive x-axis has rotated up like this, and the y direction, we rotated around the y-axis, so the y-axis is unaffected. Since the initial velocity of the proton was also in the positive y direction, that isn't changed either. So so take a moment to study that positive recording as long as you need to make sure you understand what happened here. Okay, it's really the same diagram. Basically what I'm doing is I'm looking at it from below like this. Okay. What I want to do now is a qualitative exercise. I want to ask and answer the question, what happens to the proton once it enters the field? In the previous recording, we calculated the magnitude of the force, and the force was pretty small. By the way, the force was really small, but the acceleration was very large because the mass of the proton is also very, very small. In any case, I want to analyze, though, as I say, the subsequent motion, subsequent trajectory of the proton. We're going to assume that the magnetic field is uniform. The proton stays within this uniform magnetic field the whole time that it's moving. Okay. So the proton is moving this direction. Let me maybe say this first of all. The whole purpose of this next exercise is to give you some expertise in understanding the direction of the magnetic force. It goes through the cross product. One consequence of the cross product is that the resultant vector is always perpendicular to both of the vectors that you crossed. In this specific case, we're crossing the velocity vector of the proton with the magnetic field vector that's now, as you see, pointing into the board. So our initial cross product is going to be V pointing that way, B into the board. So we're going to go V cross B, and the net force, which is the resultant vector, it's not visible here, is going to point perpendicular to both V and perpendicular to B. And so the only choice is for it to point straight upward. To put it more mathematically, the velocity vector is pointing in the y direction. The magnetic field vector is pointing in the positive z direction. The only direction the force can possibly point, therefore, is in the either positive or negative x direction, and the right-hand rule tells you that it's going to point in the positive x direction. So, key point though, when you take the cross product of two vectors, the resultant vector is always, always, always perpendicular to both of the vectors that you crossed. All right. So V cross B, when the proton is here, the force that it feels is pointing straight upward. But remember what a force does and what a force does not do. A force does not point in the direction that the velocity points. Rather, a force causes an acceleration causes the velocity to change. So since the force is pointing up and the velocity is pointing to the right, the velocity is going to be changed upward. So it goes from pointing straight in the positive y direction to pointing that way a bit. It's going to be changed upward. It's not going to go upward. It's going to be, the proton is not going to move upward. Rather, the velocity vector is going to be changed in the upward direction. And so, but the proton is still moving. And so a short time later, it's going to end up being, let's say, over there. And its velocity vector will have been changed. And so now, over here, its velocity is pointing somewhat like that. And let me put the force vector in red here. I'll make it small. Okay. Now, up here, there's still a force on the proton in this position. It's still moving. It's still a charge. It's still in a magnetic field. So there's still a magnetic force. Again, apply the right-hand rule. V points this way. With the palm of your right hand, push V, which points that way, into B, which is still pointing into the board. and then the thumb of your right hand will automatically point in the direction of the resultant force. So V cross B, and my thumb is now pointing like this, and again, perpendicular to both the velocity vector and to the magnetic field vector. Please take a moment and convince yourself that the magnitude of the force does not change. All right, but this force then, again, causes an acceleration, again causes this velocity to change, but now in this way. Okay? And so the proton continuing to move, a short time later, will be here, and its velocity vector has been changed upward. So it's pointing like that. Again, the force on it, V cross B. Now the force on it is this way. Okay, causing the velocity vector to change this direction. So, a little bit later, it's now moving like this. And the force on it points like this. Anyway, you can repeat the analysis for yourself for as long as you have patience. What you will eventually find is that the proton will trace out, as long as it's inside a uniform magnetic field, it will trace out this perfect circular path that you see there. And I'm sorry, I think I got this wrong. Yeah, that's totally wrong. What the hell was I doing? I'm sorry. Yeah, V cross B, so it's pointing like that. Okay. V is pointing this way, B is pointing, so it's got to point like that, yeah. So if I had done something like a careful job, what you would have eventually found, and you should frankly do this, is that the electric force vector is always going to point towards what? The center of that imaginary circle, and the center of that circular trajectory. In short, the magnetic force vector is pointing in the centripetal direction. Okay? Stare at that for a while, convince yourself that that's true. Once I know that, though, now I can do a thing. I mentioned in a previous recording that particle accelerators use exactly this kind of physics, and here's how it works. Now that we know that the magnetic force is acting as a centripetal force, then that allows me to calculate some things. I remind you that telling you that if I tell you that a force is pointing in a centripetal direction, if a force is, and to say the same thing in different words, if a force is causing uniform circular motion, then we can calculate the magnitude of that force, even if we knew nothing else about it, where the force came from, simply by observing the orbit that the force is causing, and also the mass of the particle that is doing the orbiting. In other words, so let me say this here, F sub B is centripetal, points in the centripetal direction, centripetal. So any force that points in the centripetal direction, its magnitude can be calculated by mv squared over r, where r is, as you might guess, the radius of the circle. Okay? In this case, the circle of the path that the electron traverses, okay? But we know this is a magnetic force, and therefore its magnitude is QV times B, and if you stare at that for a moment, you'll notice that V, in this example, V and B are always at right angles to each other, so the sine of the angle between them, sine of pi over 2 is, again, 1, so we can do this, and so equating these two, so we have QVB is equal to MV squared over R. One of the V's cancel, and we are left with the expression MV is equal to Q times B times R, or it turns out more usefully, remember momentum, linear momentum, m times v? So I can simply say P is equal to Q times B times R. Okay. The reason for this last expression, to put it in terms of momentum instead of mass times velocity, is because at the speeds that are typically used in particle accelerators, which is what we've got here, the velocities end up being very close to the speed of light, and so the kinematics here, the dynamics here, end up having to be, you have to treat them using special relativity, so relativistic dynamics. And there's a way to do that. So P becomes more complicated, everything becomes more complicated, but even so, in special relativity, the same relationship holds. And it is this relationship here, simple though the physics is, that is the basis of all modern particle accelerators. Because what they do is I mean, there are some particle accelerators where they just shoot charged particles down a long straight tunnel. But most particle accelerators build their tunnels as circles. And they immerse they put magnetic fields everywhere within this circular tunnel to create a nice uniform magnetic field. Then they fire charged particles into this so-called cyclotron. Okay, so they choose whatever magnetic field they want, and they can control that because magnetic fields are created by current. So to control the current, you control the magnetic field, both its magnitude and direction. You arrange things so that the radius of the charged particle's orbit is the radius of your cyclotron tunnel, and not the tunnel, but the radius of the so the charged particle, it can be positive or negative, by the way, but the charged particle goes around like this, nice perfect circle there, with the magnetic field immersed in whatever direction they want to immerse it. So the radius that I'm talking about is basically that radius there, okay? And then you can do anything you want. If you don't know what the charge is, you can rearrange this equation and measure it. If you don't know what the particle's momentum is, you can just solve for it. If you want to know just its mass or just its velocity, you can do that. I mean, lots of things. And in any case, this particular relationship, because of all this, because of how it's applied in modern day cyclotrons, is named exactly that. This is called cyclotron formula. And it is fantastic in both the depth of the physics that it allows and the simplicity of the physics from which it comes and the almost triviality of the equation itself. So very, very useful, very, very powerful, very, very understandable, and pretty cool. So that's the end of that. So what we're going to do in the next recording is discuss the magnetic field, where it comes from, how to calculate it, and related matters like that.